Every supply chain operation exists to solve a single continuous problem, maintaining the exact equilibrium between the physical supply of goods and the market's demand for them. Get this balance wrong in one direction, and you overstock. Millions of dollars of operational capital end up trapped in warehouses, gathering dust instead of generating returns. Get it wrong in the other direction, and you face a stockout. These empty shelves represent immediate revenue destruction, breaking customer trust and driving buyers straight to competitors. Global networks cannot rely on reactive replenishment to mitigate these risks. By the time you notice an inventory imbalance, it is already too late. They require a forward-looking predictive mechanism. Look at sudden demand spikes, like holiday rushes. Standard reactive ordering systems collapse under this kind of pressure, without a model projecting the volume weeks or months in advance. Operating without a forecast guarantees one of two outcomes: wasted capital or lost sales. It acts as the ultimate financial shield in operations. In the APIC supply chain framework, forecasting is defined as the rigorous process of estimating future demand variables based on historical data, patterns, and assumptions. The foundational axiom here is that forecasts are entirely probabilistic. They are mathematical estimates of what might happen, never exact guarantees of the future. We must clearly separate the passive act of forecasting from the active act of planning. Forecasting asks, what do we think will happen? While planning asks, what will we do about it? Demand planning is the distinct step where that objective mathematical forecast is combined with subjective business strategy to create a concrete action plan. Whether a supermarket is projecting the volume of milk sold next week, or a factory is projecting demand for 10,000 widgets next month, the underlying mechanism remains identical. Forecasting provides the objective data foundation upon which all subsequent operational decisions are built. A functional forecasting system operates as a continuous living loop, rather than a static annual event. The architecture begins with the inputs phase, gathering historical sales data, broader market trends, and specific seasonality factors. This data then enters the methods phase, which splits into two distinct branches: qualitative approaches relying on expert judgment, and quantitative approaches using mathematical time series models. These methods converge to generate the output, a single numeric target for the upcoming planning cycle. But the cycle doesn't end there. The most critical phase is the feedback loop, where actual, real-world sales are compared against the initial forecast. The mathematical delta between the initial prediction and the actual observed reality is known as the forecast error. By rigorously measuring this error, quantitative models can self-correct, adjusting their algorithms to improve accuracy for the next cycle. A forecasting model's true strength lies in its structural architecture that continuously learns from its own errors over time. There is a primary operational paradox at play here. Forecasts are always wrong, but they are useful. The mathematical goal is strictly about minimizing variance, not achieving perfection. This brings us to the principle of aggregation. Predicting total demand for an entire product family is statistically much safer and more accurate than predicting exact sales volume for one specific item. This chart illustrates the principle of time horizons. Notice the widening cone of uncertainty. Prediction accuracy rapidly degrades as the timeline extends further into the future. We map these horizons directly to business functions. The short term drives immediate operations, the medium term informs sales and operations planning, and the long term dictates strategic investment. Because of this built-in mathematical uncertainty, forecasting cannot happen in a silo. It requires cross-functional collaboration between sales, operations, and finance to reach a consensus. Successful supply chains do not attempt to fight mathematical uncertainty. They structure their planning horizons to absorb and manage it. Once finalized, this forecast acts as the primary input for sales and operations planning, driving alignment across the entire company. The calculated forecast error directly dictates inventory planning, specifically determining exactly how much safety stock must be held to buffer against variance. Capacity planning relies completely on the demand forecast to allocate human labor shifts and schedule machine operational hours. Every physical action in a facility, from purchasing raw materials to dispatching a freight truck, is anchored to this single predictive estimate. Real-world execution is constantly threatened by external shocks. Pandemic-driven demand volatility or rapid market shifts can instantly invalidate a model. There are also internal threats that corrupt the system, specifically poor data quality and the cognitive bias of over-optimistic sales teams inflating the numbers. These errors generate the bullwhip effect. Tiny forecasting errors at the retail consumer level amplify exponentially as they move upstream through the supply chain. The operational consequence is devastating, resulting in the massive overordering of raw materials and severely overloaded manufacturing capacity at the supplier level. Untreated forecast errors do not remain localized. They compound aggressively, ultimately destabilizing the entire global supply network. Modern technological trends are designed to combat this friction, starting with real-time demand sensing at the point of sale. This chart shows how machine learning algorithms ingest massive, non-traditional datasets to detect complex purchasing patterns that are invisible to standard regression models. Integrated planning systems ensure this real-time data is instantly visible across all departments, preventing isolated information silos. Ultimately, forecasting is the vital bridge connecting historical data to future operational readiness. The professional goal is never perfect prediction. It is creating a resilient architecture that can pivot dynamically based on changing probabilities. Masterful supply chain management is defined by the rigorous execution of the plan, guided by the continuous, humble refinement of the forecast.